thanks the organizer for having me here, for the opportunity to present some of our results here. And I feel privileged to be part of this meeting, whose part objective is to honor Chris and Chandan for their scientific achievement over an illustrious career. Both of them inspired a generation of students, including myself, and I wish them success in their future journey. Thanks, Chris and Chandan. Okay, so the talk title is Spatio-temporal correlations across melting of 2D Wigner molecules. I'll explain at least these words, which might be a little uncommon. So this work is driven primarily by my PhD students, Vishwarup Ash, and we certainly have other collaborators whom we acknowledge towards the end. But let me put down the theme of the talk. So we will be looking at Coulomb interacting particles, that means long-range interacting particles in two-dimensional confinements, and we will study the static and dynamic responses of a system made of these particles across melting. So whatever that melting in quote means will be clear. The objective will be to understand the spatio-temporal correlations in systems whose size is of the order of range of interaction. So that's something that is important, and that's the focus that we want to explore. And then we'll try to understand the effect of disorder, which is in the form of some irregularity, which will also become clear as we go along. So the effect of disorder on this study, correlations for these systems. So, the study of long-range Coulomb interaction among particles, particularly electrons, started at least from a certain perspective long time ago by Wigner, where he said that the Coulomb repulsion will force a particle, for at least for a low density electron gas, to stay as far apart from each other, of course consistent with the density of the particles in the system. So in the extreme limit where kinetic energy is completely quenched, they will arrange themselves because of this repulsion in some kind of a regular periodic pattern, and such objects are called Wigner crystal. Okay, so now if you introduce kinetic energy will delocalize them and can even cause the melting of such a crystal across at some threshold value. So this is for two-dimensional system where we will focus on, the crystal is actually a triangular crystal. The Bravais lattice that minimizes the energy is a triangular lattice. So now, as I said, so kinetic energy, by tuning kinetic energy, you can achieve this melting in the bulk system. So that kinetic energy can be supplied for a classical melting by temperature. So this is just a regular thermal melting, and I will be focusing mostly here. And then we will probably have little bit of time to touch upon what happens when this kinetic energy is supplied by the 0-point motion, which is indeed the quantum melting, and that is what Wigner actually started looking into. But there is a classical version also, which is what we will be focusing on primarily. But after this slide, I will not be talking about bulk system at all, but instead we will focus on what are called Wigner molecules, that is a finite version, a confined geometry of Coulomb interacting particle, and whatever is the structure at the low temperature phase of these electrons or these classical particles within the trap is what are called Wigner molecules. So it's the finite system version of a Wigner crystal. So crystal to molecule, just the name that way. So these are very popular because mostly to do with the experimental tunability, for which Wigner physics is probably better studied in this finite geometry. I mean, that's just a matter of technical advancement. So there are many different systems where you can achieve these Wigner molecules. So one of them I showed here as a cartoon. So this is dusty plasma. And so what you do at very low temperature, these are like trajectory of electrons. So you have trapped these electrons, trapped this plasma particle, highly charged plasma particles in a circular confinement, and then you tune them by laser and thereby induce melting as you go along, changing the laser power, things like that. So this is something which is indeed accessed in experiment. And this similar thing can be done over a variety of other systems, radio frequency traps, Wigner crystal on helium film, which is done in IISc by Ambarish, many of you probably know. And then also in, and probably people believe that it could be achieved in quantum dots as well. So now there are interesting dynamics that can be also accessed in confined system, not always necessarily Wigner molecule, in the sense that there may not be always long range interacting particles. Like for example, you can take air driven steel beads where you can see, I mean, these are color coded depending on the mobility, and you can see what is called a dynamic heterogeneity, clumping up of particles with different mobility in different regions of space. You can have relaxation of localized stress in 2D colloids and so on and so forth. So these are sort of the motivation, and with that, yeah. You don't require if you trap them because they're not flowing out to infinity anyway. You could have that. In a bulk, you must have that. In confinement, you need not. There is no screening that is assumed, yeah. Or, yeah, so there are many reasons I can sort of motivate that small system, very finite number of particles, low density. We can talk about that, how good that is. But the point is that we still need, I mean, we want to see the long range interaction effects. So, right, so that is true. That is true. So they take Yukawa most of the time. Yeah, so the question is whether that will make them, so I want to make a distinction between short range and long range. I mean, that is so depending on how screened they are. So I mean, if it is, I don't think qualitative physics will differ too much from Coulomb if I go to dipolar and things like that. That is still long range, perhaps. I mean, that's something that we are looking into now. I mean, how the range of interaction changes whatever we are going to talk about now. Okay, so what we have, I mean, this thing I said about the objective. So what we wanted to do, I said that we wanted to study the effect of disorder. So we will take some potential like this, which is something like this, and we have squeezed it in some way, so that our Hamiltonian has this Coulomb particle and the confinement that I am plotting here is given by some complicated looking function. So why I take that? Because I want to take something which mimics the effect of disorder. So for example, there are potentials that probably there could be several others, but at least this is one kind of potential that has been studied in literature in quite details by doing various things. For example, one had looked into the dynamics of single particle within a trap like this, so whether that can give a, so in potential like this, you can tune it to go from completely integrable to fully chaotic motion, and that chaotic motion is taken to be a signature of disorder, for example. Okay, so now you can do that by tuning these different parameters, which is lambda and gamma, and this potential breaks all the spatial symmetry. That is also another important point. And then you can tune the parameters that you have here, and thereby you can sort of match the same chaoticity by having different parameters, and thereby you produce self-similar realizations over which you will do disorder averaging. So all that has been done in the past by people. And that's why we take that. There could be various other potentials which could do all of these as well. However, what we also do, we always compare results with a circular confinement, which is the most symmetric one that you can have as a confined system in 2D. So that will tell us probably something about the effect of disorder. And then the computational tools are very standard for classical, and for quantum we developed and developing some Monte Carlo techniques. So at the very beginning, let me tell you the picture of what is melting here. So I start with the particles. So these are like the snapshot of particle trajectories over a length of simulation for low temperature, intermediate and high temperature. So at low temperature, all these particles are rattling around their equilibrium position, and I call them solid. And then as you increase temperature, they will melt. So this is what happens for the standard symmetric potential. So now if I switch on my trap, I mean the irregular trap, this is how it goes towards melting. So what is very interesting, I wanted to sort of emphasize right at the beginning, that we see some kind of a signature of incipient melting that is happening in some region of space by making tortuous motion of particles over some long path, and then finally it melts. So this is not to say too much, but just to get a pictorial idea of what melting we'll be talking about. So the first question that we must address is how do I define the solidity in an irregular confinement? So it's some kind of amorphous solid we have. So it's sort of obvious, I don't have to work too much to give you the impression that there should not be any positional order in an irregular trap like this, and that we can check. I mean, one can take a look at a structure factor, which is a lot more diffuse compared to what you would expect for a perfect triangular lattice. You can make it look little better by taking the central region, I mean, staying away from far, but even then, just with naked eye, you can see that there are lattice lines which are wiggly lines, so symmetries are broken, positional order is broken, so this is the corresponding structure factor, and there is hardly any temperature dependence of rho of k, so that gives an impression, that is sufficient to say that there is no positional order. So you can do the same thing for circle, and you can see there certainly lies slightly better order because of the symmetry and so on and so forth. So what is that defined solidity is what I will take as what is the second order that people talk in two-dimensional system, that is the bond orientational order, which is defined in a certain way. So all that it says that this is the propensity of having a 6-coordinated neighborhood for triangular lattice where two successive neighbors of a particle makes an angle of 60 degrees in the perfect situation. So that order, I mean, if you wanted to take a distribution of that over every particle, so you can define it for every particle. So for a triangular lattice, that will have a delta function peak at the value of 1. I mean, this is constructed such that the value becomes 1 for every particle in the perfect triangular lattice. So for our case, so here for all the results where I will have the irregular confinement on the left side and regular, meaning circular confinement on the right side. So for both we see that there is indeed a very sharp peak at value 1, and then as you at the lowest temperature, and as you increase temperature, this distribution broadens, and then finally it goes to a situation where there are random angles where things are completely melted. So a little better way of, yeah. This is a local bond orientational order, and we are plotting the distribution over all the particles as well as this. And the very next figure, I'll say that, so now you can ask, can you do little better? Can you identify a crossover temperature? So the thing to look at is the bond orientational correlation function. So what we do is not really the full bond orientational correlation. So what we ask is how much does the bond orientational of this particle fits with the bond orientation, average bond orientation of all the neighbors. If I had taken it over all the distances, that will be the real bond orientational correlation function. So the advantage of this thing is that when there is no correlation in the liquid, that will have a peak towards 0. However, in the solid, when there will be a orientational order, there will be a peak towards the value being 1 of this object, and you can sort of identify the temperature where you go from one mode to other bimodal structure as the temperature, crossover temperature. So every time I talk about melting, I actually mean a finite size crossover, because that is indeed what it is. So one can look at the Lindemann ratio, the very standard identifier of melting Lindemann ratio. One can look at the peak in the specific heat. What turns out by looking at all that, all these are giving me a value of crossover temperature which is within tolerance, good agreement with each other. And that had been studied over other variables as well, some generalized susceptibility, full correlation, long range correlation, within long range in the sense of the finite system. So all that. So the take-home message at this point is that the crossover from solid-like to liquid-like behavior can be discerned in this object, number one. And what is probably I didn't emphasize is that much, that the crossover like this temperature scale is not so much dependent on whether the geometry is circle or it is irregular. Okay, so so there is not much difference within the error bar; they are similar. And then what was also found that qualitative responses are more or less independent of n. I mean, there are some dependence, there are some details, but essentially, unless the system is too small, when your number of particles on the boundary is too large compared to the number of particles at the bulk, I mean too large meaning of the same order, then of course there are things which are not generic. I mean you will not see generic behavior, but this is a good range where many things you see sort of generic behavior. So now, okay, so that was the static. So what can dynamics, at this point we asked what can dynamics tell us about the solid and liquid states in the trap? All the solid and liquid within quotile is often just to emphasize that these are not truly a phase, this is the confined version, and I guess that is understood. So can motional signature distinguish the crossover based on the nature of the confinement? Can it distinguish the irregular versus regular? And more importantly, can we access generic signatures of disordered dynamics in traps? So is there some generic feature of dynamics in disordered system? This part will be clear as we go along. So these are the questions, and you can think this is as the outline of the rest of my talk. With that, let me make progress. So at the outset, let me tell you the result of simulation. I mean, this is the raw data from simulation where what we are trying to show is to emphasize the dynamics in this system, let's say the irregular system. So what we are showing here, this is at a very low temperature, which should be a solid according to the static characterization, deep solid. So we are showing the displacement of particles after a time step of 100, which is a small time step, and not so large time step. So what I show here is dots at the initial position of the particles, and then they are joined to by a stick to the final position of the particle after a time 100. Okay, so that's this picture means. So here it is 1000 and here it is about 10,000. So what is to see that for small times at low temperature, particles hardly move, they're caged or they're locked in their position by the repulsive neighbors. However, what is interesting to see that there is some development of little bit of motion which are lined up. So that actually grows in size in the sense that what happens around some time, which is little largest time, what happens, these particles, which after some time, there is a finite probability that this particle will jump out of the cage. So the moment it jumps out of a cage, it must fall into a cage of another particle, which will be very unhappy because of this Coulomb repulsion. So that will jump out, the next one will jump out, and that way it will produce a motion over little largest distances over, a tortuous, a spatially correlated motion in a tortuous path of macroscopic sizes. Okay, so this is what happens at this stage, and then if I wait for longer, then it turns out that this tortuous motion, this correlated motion grows in size and then breaks down into smaller and smaller region inside the trap, and they perform their own sort of correlated motion in that region. So this is something which is often referred to as dynamic heterogeneity. The dynamics is very heterogeneous depending on the region of space. The color coding of the particle just to say what their mobility is, and this is probably easy to follow. The green one is little higher, the higher mobility than red one, and then blue, and then higher and higher mobility. So instead, if we look at the circular potential, so there also this correlated motion, spatially correlated motion lines up, but that is now dictated, where it will happen is dictated by the symmetry. So this is sort of obvious. So the question is, what are the concepts? So I wanted to emphasize once more that this kind of motion is very different from what you would expect from, let's say, a harmonic theory of melting. I mean, the kind of Lindemann picture. So this is very inhomogeneous. So then what we went ahead and explored that what are the consequences of this kind of a motion on various physical properties of the system, and we'll focus on that for next few slides. So so before I move forward, I must draw your attention, and many of you in the audience know it better than I do, that such kind of a spatially correlated motion has been found in various different systems. Yeah, please. No, so this is, yeah, so if you have a particular configuration of the potential, they typically come at the similar place, right? Yeah, so that way this is the effect of quench disorder, where they will occur, yeah. Okay, so now there's the first standard thing that you would calculate in this business is what is called the self part of the Fanhoff correlation function, which is a density correlation function. It gives the probability that by what distance, what is the probability of the particle to move at a distance r in time t on an average, right? So this, I mean, if it was a harmonic theory, you would have expected this to be a Gaussian decay, right? I mean, the probability at a given time, I mean, all these are given time, at a given, I mean, each color represent a particular time, and then this will fall as a function of R in a Gaussian form. So this is indeed what happens at the lowest temperature, but then as you increase the time, there are temporal regime that you can easily define, you can easily identify. So it very quickly it goes from, and this is in a log scale, it goes from Gaussian to something which is exponential, and then it becomes even slower decay, and then finally at very large time it shows bumpy structure, I mean non-monotonic behavior of this, and that's actually true for both these things. In between it shows a Kejim regime, which means that over a period of time there's hardly any change in this, I mean because things are caged, so you don't expect that. So this quantity are experimentally accessed, so that we are not going to talk too much more about. So this is for irregular, this is for regular, as I said before, I mean it will always be left is irregular and right will be circular. So what is interesting that now, so that was for a low temperature. If I go to high temperature, this trend continues in the sense that I mean this decay becomes very, very slow. I mean the spatial decay as a function of R becomes very slow and we'll quickly quantify. So this is a little surprising in the sense that when you look at the displacement, they're completely random. Still, when you look at this GS, it seems to defy this central limit theorem or law of large number. Okay, so now we wanted to quantify this decay in the sense that because the decay becomes very slow, so we would like to sort of try to fit them in the form which is e to the r to the some power k. So with the motivation of trying to get some kind of a stretched exponential behavior. So we tried various different fit. And then I would also mention that this thing is done in a systematic manner by determining what minimizes chi-square, which fit we choose the best one. So if we do that, what we find is something interesting, that for smaller times, and this is expected, the power is 2. So power 2 means it's a power 2 means it's a Gaussian decay as a function of t. So what let me pause a bit and try to make it a little clear. So what I am plotting here is power k as a function of time for different temperature. All these different color traces are for different temperature. So let's take the lowest temperature, which is red here, where it means that the power is 2, that means it's Gaussian up to this point of time, then it becomes slower, and then it saturates to a value which is exponential decay. So that is true for both irregular as well as circular. The red plot here saturates to something close to 1. And this is something what has been proposed as a generic behavior for glassy systems. So now what happens is, interestingly, what happens as I increase temperature, this thing becomes slower and slower. I mean, basically this value of k, the power, to become smaller than 1, that means I am accessing stretched exponential decay of a spatial correlation function. So that is perhaps quite interesting. You might ask that, and just to contrast, I will say that in a circular trap, that always remains somewhere between 1 and 2. It doesn't go down. It doesn't go to a stretched exponential decay. So now you might ask that, this cannot be true, because if I go to very high temperature, then I must recover, or probably I hope to recover the Gaussian behavior at some large temperature, the usual liquid, garden variety liquid. So indeed that happens. So what turns out that this number starts decreasing and go to a smaller value up to like 0.4 at a temperature which is the crossover temperature that we found from static. And then it starts increasing very slowly at long time and it achieves the value 2, but at a temperature which is here, which is more than 10 times larger than the melting temperature. So there's a huge window of temperature where the liquid behaves like a very, very strongly inhomogeneous liquid. Okay, so now, so let us, so what we did, yeah. Because if the temperature is very large, I would expect it will average over all the inhomogeneities and give a Gaussian behavior. I mean, if it is a diffusive liquid, then I would expect it to be 2. Sorry? Okay. Okay. So then we have looked into various other correlations, which I'm not showing here. So we have looked into standard ones like mean squared displacement, study of mean squared displacement to understand the Fickian yet non-Gaussian behavior here. We have looked into how the propensity of this 6 coordinated neighborhood, which defines the solid, decays in time. So if you are interested, we can discuss that. But rather than going into, going into those, let me try to extract, because we are talking about dynamical heterogeneity and all that, which means that you have multi-scale relaxation in the system. So let us try to extract some of the time scales that people often talk about. Okay. So with that motivation, the first thing we try to look into is what is called the overlap function. So what it basically, physically, there's some mathematical formula, but essentially what it means that if a particle moves out beyond some cutoff distance, then you will say that the structure will relax, associated structure will relax. If many particles start doing that, you want to look at the average behavior of that function as a function of time. So again, this is the irregular, this is the circular. So it turns out that they fall, and the fall, okay, so we'll talk about the functional dependence a little bit later, but we try to get the time scale associated with this, which is a structural, often called a structural relaxation time, by equating this value to 1 over E. This is just one way of getting it. And so because, we are doing this because our system is finite with finite number of particles, irregularity and all that. Otherwise, you would ideally get this particular time scale from the intermediate scattering function. So, okay, so now the next thing we look into is is what is called the dynamic 4-point susceptibility, which is actually the fluctuation of what we calculated before, fluctuation in Q. Okay, so what you try to say is that this, so if you think that the particles, all particles are, if you are looking at so this is as a function of time, so at very small time, there is hardly any fluctuation in Q because no particle has moved by any appreciable distance, and this chi4 will be 0 because these two will be equal. Chi4 will be 0. Similarly, if you waited for a very, very long time, every particle moved out of that cutoff distance, again this fluctuation will be 0. So in between there will be some time when the fluctuation will pick up a maximum value. So that is often identified as the time scale for dynamic heterogeneity because of this fluctuation. So what we wanted to get is what is that time scale. So you can see that there is a maximal value for each temperature, and then you can look at the temperature dependence of this tau x, and that grows as you go to lower and lower temperature. Then you can look into another quantity which is called a cage correlation function. So essentially what it means that when particles rearrange when they are moving, so the system relaxes and particles diffuse. So you start from a given time, you had certain particles as your neighbor. As time progresses, some of them will no longer be your neighbor. So how does it evolve with time? In the sense that so what we do is we take such statistics over all particles and over all the Monte Carlo or molecular dynamics steps, and then find out how does that correlation, decays with time, and that we found to decay as kind of a stretched exponential form. Don't take these numbers very seriously. They are similar, but there are some end dependence and so on and so forth, which we are not talking about here. So, but the point is that you can calculate or you can extract some time scale from there too, encoding some relaxations in the system. We also looked into what is called persistence time and exchange time. So again, the way I should at least give you the idea of what this is, persistence time is when a particle moves out beyond a cutoff for the first time, and then exchange time is after the particle has moved out beyond that cutoff distance, what is the time it takes for the subsequent moves by that much of distance. So why it could be important? So for a system which has dynamic heterogeneity where some particles are moving very fast, some others slow, so then you can easily see that this persistence time and exchange time will be very different, can become very different, right? So this is precisely the point. So what we plot here is the distribution of persistence and exchange time for different temperature. For a particular temperature, the dashed line is the exchange time, and the solid line is the persistence time, and this is what is the distribution in log of that time. So what we can see that that as you go to lower and lower temperature in irregular confinement, which is the one which we call with disorder, these two starts decoupling. Actually, this starts decoupling at the temperature which is roughly the temperature where we see the crossover from solid-like to liquid-like behavior, and that continues for lower temperature. I mean, I don't have lower temperature data here. However, on the other hand, at least this temperature, you can see that for circular, there is hardly any difference in the two distribution. And again, this distributions, matching to distributions requires some statistical test, and that has been done on the results that we have. So, okay, so the other time scale, I mean, this is sort of an obvious time scale. You can calculate a caging time. So basically, when a particle is caged by its neighbor in a perfect lattice, you would expect that distances of that particle with all the vertices, all the other particles are same, right? I mean, in the ideal, I mean, let's say triangular lattice. So now that will certainly not be the case as you switch on temperature, and there will be fluctuation. So and then you put a cutoff that if the fluctuation is beyond some point, the particle is no longer caged. So if you do that, and then you will say that you will also define something which is, and there is some marker which is given here, how much fluctuation. And then you will say that once the particle is not caged anymore by our criteria, then the time it takes to become caged again is what you call non-caging time. And then for every, so these are for different particle numbers here for irregular. So what I'm showing here, the solid line is the caging time. So of course, caging time will decrease as you increase temperature, because the concept of caging will become weaker, and the non-caging time will increase. The dotted line of the same color is the non-caging time. And if you see that they are appearing to cross over again at the same crossover temperature where we found the melting or the crossover from our statics. There is some independence that we see here. The crosses are not exactly at the same point. Nevertheless, I mean, so this is also nice to see that from these dynamic quantities, the extraction of the crossover temperature was pretty nice. So with that, the last part of the talk, I will spend on maybe 5 minutes on something which is ongoing research, and this is the normal mode analysis. So this is also somewhat half-cooked in Hassan's language, but I'll still try to hope to give you a flavor of excitement in the thing that we see. So first day of the talk, Abhishek discussed about normal modes, but let me quickly give what it is. So this is actually normal modes gives you the dynamic response. I mean, how each particle proposes to move in a given configuration when they're performing a collective movement. Like this is something which you know from phonon in our first course on condensed matter. So now for this two-dimensional system, what we do is the standard procedure of constructing Hessian matrix with instantaneous configuration of particle for the n particle, and we look at their eigenvalues and eigenvectors, and we do the analysis. So now what we are showing here is the density of state distribution of normal modes, density of state. So the first thing to notice here that there are few features that I wanted to draw your attention to. So now at the zero temperature, you cannot have a negative mode. So what does this negative or unstable modes mean? They mean that there is a potential hill over which the configurational transitions are taking place. So of course at zero temperature, you could be in a at least local minima for all particles. So you could have all these things, all the eigenvalues, all the omegas positive. So now as you increase temperature, your transition in the configuration space increase, and you develop some weight to the negative modes. So now you can take at the ratio fraction of modes, I mean unstable modes, and that can give you an idea of how the melting is occurring. We have looked into that. One can also look into participation ratio. This is the participation ratio that I am plotting here. So that will mean that which modes are delocalized will have a large participation ratio and vice versa. So what is very interesting to see here in this, that there are very strong fluctuation. I mean, peak dip structure that you see both in the density of state as well as in participation ratio. So in finite system you will expect some fluctuations, but then there are some fluctuations which are robust, and I'll try to impress upon you that there are some robust features that we find, but then there will be something robust features which are probably related to what I call mesoscopic fluctuations in a confined system. So before I do that, so I'll say that there are very, very sharp modes in circle, but that is understood. I mean, they're just symmetry modes. So for example, modes like this, where there is a bodily motion or sloshing movement or breathing mode, they will involve ball particle, and we'll have very large participation ratio as well as large peak in the circular case. So what causes this somewhat sharper peak in the irregular case? I'll not have an answer, but I'll try to say something. But I wanted to also tell you that normal mode analysis can be done in the inherent structure space, so where you look at the energy minimized configuration. So if you do that, here there are some particles trajectory that was in the actual time dependence of trajectory which was there. In inherent structure space, it just removes vibrational motion and they take out the long distance long displacement in the inherent structure space. And you can also look at with this quench, these are called quench normal modes, the energy minimized structure. So there you can also calculate rho of omega and IPR, PR, I mean participation ratio. So now let me try to show you how robust are these peaks. So here I take a particular system, instantaneous normal mode, some temperature, and this is the main feature that I see at low frequency. There are some modes which are showing peak. So now I go to a little lower temperature, I see the peaks at the same place. I go to higher temperature, I see the peak at the same place. Other features are disappearing, but then there are some which are really robust to temperature. I can do even more. I can go to quench normal mode. I can plot they're the same peak at the same point, right? Now I do even more. I go to a system which is much larger. So number of modes are now very different, binning is very different, but the feature still remains that these 4 peaks are still at the same place. I go to even larger temperature for 500 particle system, they still live here. So and then these results, some of which had some level of averaging done already, not only over different molecular dynamics run, but also over different disorder realization. These peaks appearing to be robust to all of that. We don't have an answer to this, why they're there, but this is something which probably requires some understanding. One can now look at the overlap function that I have done before, but plotted in inherent structure space. So one can fit it to this turns out to be fit well by stretched exponential, except for this very small value. This we didn't try to fit even. And this tau dependence, the corresponding tau, the time scale, appears to follow power law behavior with a power of about 4.5 or something. Then the final part that we looked into is try to ask this question, this is ongoing, can we construct the long time displacement from the normal modes calculated at the initial instant? So you have long time displacement, can you predict what the long time displacement will be just by looking at the normal mode at the initial instant, energy minimized normal modes at the initial instant. So to do that, low-lying modes, just looking at low-lying modes. So to do that, what we plot here is look at the system and we color code them with the mobility. So we try to identify the fast moving particles which have this yellow or brown, this kind of a color. And then on the right side, what we ask is what is the sum of the low-lying eigenvectors? This any is a finite fraction, and we will look. This is the eigenvector sum over some finite number. I'll tell you what the finite number and how does that look in a color-coded manner. Just the magnitude. So basically, try to see the close connection between dynamics of particles and properties of the inherent structure, as I said before. So now what I do here, I just look at the top 10% of the fast particles. And here I look at the top 10% of this eigenvector sum, the mode sum. So that is a finite number. So when I do that, then so only those particles are now color coded here. Colored here. So now what is called a region of propensity is what is the match between the two. spatial match, and and it turns out that when I plot on top of each other, there's a large correlation, large spatial correlation between the two of them. And then what we have been studying is their dependence on various delta t. So I forgot to tell you. So here delta t was only, I mean, this is not relevant for this side. This is the displacement after time delta t. So that's where we are looking into. So now we can change that and we can see. So it is expected to go down again if I take delta t to be very large. I mean, so simply because it will be decided by some other, I mean, a very long distance move. I mean, after a long time will be decided by some other inherent structure. So that was basically the talk, and I have exhausted my time. I don't have any time to tell you about quantum problem that we have started looking. So I'll just flash this transparency to give you an indication that now we can look up this thing both as a function of temperature. So at very small n is the quantifier of the quantum fluctuation in this case. It's not just the density. I mean, this is our symbol. So this is what we have been talking so far, and now we can increase the quantum fluctuation this direction and melt the Wigner crystal here, and now we can see I can, in principle, I can study the whole space. So we have several questions to address related to this, which we'll be doing, and I'll just acknowledge my collaborators. So as I said, Vishwarup, who did much of this work, is, it started with my first student who is now a postdoc. Vishwarup is also leaving for postdoc after some time. And then Anurag is looking into the quantum problem that we want to develop. And here the senior collaborators, both of them are in the audience. We benefited to develop our quantum Monte Carlos by interacting with people from the Hill group. And we benefited also by discussions with Deepak at EIFR, now in Pune. And I leave the conclusion slide here, and I thank you for your attention, and I'll be happy to take up questions now.
So the displacement distributions in different parts of the system, they are not identical. So this
right. So that will reflect if I look at very long time.
Yes.
So that also can be understood. I didn't talk about it, but I can understand basically the bump, they will cause the bump structure at very long time.
So the central limit theorem should not apply?
No, so it will be a non-Gaussian, yeah.
Yeah. So, yeah.
So this is actually the statement that people often talk about, often mention, that Fickian yet non-Gaussian behavior. The point is that GSRT is non-Gaussian. But if I wanted to find out what is mean squared displacement, I can multiply it by r square and take an integration over r. And then what I have is mean squared displacement, which is a function of t. That will still be Fickian in the sense that will be m square. This r square will still go as t. So yeah, so GS will be non-Gaussian, but m square, not m square. The r square will be Fickian. Yeah. What is the
Source of the Fickian but non-Gaussian.
Source? Yeah. So it's a disordered system. So source is essentially, so what is non-Gaussian, I can try to explain, and that is what I said at the beginning, that the motion is certainly not Gaussian. I mean, if you expect a Gaussian, at least the standard way to get Gaussian is the harmonic theory, right? I mean, everything is displacing little bit, and as you increase temperature, they will be displacing little more. I mean, the size will increase, but still remain Gaussian. But here what turns out is that certain particles are moving in a very different manner, so it's a dynamic heterogeneity essentially.
So Amit, unlike a lot of systems where people look at these, in your system where you see heterogeneity, you have actually a geometrically defined heterogeneity.
Right.
So if you actually sort of look at dynamics in the different regions,
right,
then does the picture simplify, or do you still have something that's sort of complicated and interesting?
Right. So this we wanted to do and we are doing, but the thing is with the kind of number that we have, it's not very large to look region-wise very clearly. I mean, they're already small systems, but we are trying to get at that.
So the second question is in terms of these densities of states that you had these peaks.
Right.
At least I didn't understand if you offered an explanation, but the
I
question
didn't offer
is,
any explanation for the robustness of these peaks. I just.
But I mean, is there, if you have a system with fixed boundary conditions, you should have some standing wave type of modes that get enhanced or not? I don't know. But maybe not. I
mean, I don't really have an answer to offer right away, but we can discuss further. That is what we are looking, and we couldn't find anything which stands out, yet.
The trap potential seems to have at least one axis which almost has a reflection symmetry. It is not completely devoid of all symmetries. It seems that this axis has a reflection symmetry.
All symmetries are broken because if you, I mean, basically there is a term which is x, y, I mean, so.
At least visually, it seems that if I reflect along the diagonal.
Which diagonal? Tell me.
No.
This one?
Yeah. No.
Left, this one?
Yeah.
No, this is not. I mean, this will not fall on top of each other. I mean, maybe,
it's almost a symmetry, maybe only partially broken, that might.
Yeah, but so the thing is, I mean, the results, I mean, when I have to show this result, I can only take one configuration, but all results are averaged over 6 different potentials like that, and there is no symmetry which is there. I mean, there are explicit terms in the Hamiltonian I can refer to you which will break the symmetry, but.
So if there are no more questions, let's thank Amit again.
Thank you.